Okay, good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. Today in this lecture, we are going to discuss about a new topic, that is quantum mechanical scattering and tunneling by one-dimensional potential step. So here scattering means it has to be one type of, you can consider the so-called diffraction or reflection from an object. Okay, so this scattering is going to be observed, scattering as well as tunneling through a potential step. So before we have to start, first we have to just go through the what do we mean by potential step. So the diagram figure or the figure 1 represents a one-dimensional potential step. That means here this is from minus infinity to plus infinity along x-axis, and here this is Vx at x is equal to 0. So at x is equal to 0, what happens? That potential is suddenly increases. Means before x is equal to 0 there is no potential. That means Vx equal to 0. But exactly at x is equal to 0 and onwards up to x equal to infinite, the potential value is V0. That means at x is equal to 0, the potential suddenly increases to V0. Before x is equal to 0, the potential is 0. Exactly at x is equal to 0 and beyond that, the potential is V0. So in our previous class, we have been discussed that the so-called potential means one type of, you can think one type of repulsive force. Suppose here one positive charge is moving along this direction, freely it will move up to x equal to 0. Okay, exactly at x is equal to 0, that charge is going to perceive a repulsive force. That means you just imagine that at x is equal to 0 and onwards, a large positive charge will be situated. So when this positive charge, small positive charge is going to be reach at x is equal to 0, it will be perceive a highly repulsive force. That value is nothing but V0. Okay, the magnitude of V0 repulsiveness or repulsive force, this particle or this positive charge is going to be perceived or going to be found at exactly at x is equal to 0. But from minus infinity to up to x is equal to 0, that positive charge moves freely. There is no interaction, there is no force from minus infinity to x is equal to 0. But exactly at x is equal to 0, suddenly a repulsive force, that charge particle is going to be observed. So this sudden change of force is nothing but the so-called potential step. And also in our last class we have been discussed that the so-called potential, here you can see the so-called potential or potential energy is derived from the force. That means here dVx will be equal to f dot dx, means we can say that f will be in the form of dv by dx, like that. So the so-called potential will be in the form of force into displacement. Means if there will be a force is going to be exist, that at that point the so-called potential will be developed. So here due to a large positive charge, a repulsive force is exist here in this region, but in this region there is no potential or there is no force, we can assume. So this is represented as region 1 and this is represented as region 2. So in region 1 the particle moves freely, but region 2 exactly at x is equal to 0 and onwards, it perceives or it found a force or a force with magnitude or potential equal to V0. Okay, no need to draw this charge symbols. Only you have to write region 1 and Vx equal to 0, and region 2 this Vx equal to V0. No need to draw this figure. Only for your understanding purposes I drawn here. Okay, so this charge things so no need to write, no need to draw. Only you have to write region 1 and region 2. Okay, so whatever we have been discussed, that things here it is written. Only I am going to be read, you just watch. If potential energy of a particle suddenly changes, so here potential energy, or there is no force field in this region, so but here at x equal 0 and onwards, suddenly a potential or potential energy is increased. So if potential energy of a particle suddenly changes, change from one constant value to another constant value, here Vx value is 0, here Vx equal to V0, constant value is 0, and here changes to V0 value as shown in the figure, then it is called as a potential step. If a potential step occurs at origin, the mathematically it can be represented as Vx equal to V0 for x greater than equal to 0, greater than equal to 0, and for x less than 0 it will be 0. For x less than 0 the Vx value is 0. Okay, so that is potential vanished to the left of the origin, what we discussed now, that left of the origin, and attains a constant value V0 to the right of the origin. Okay, here we will discuss two cases. Now we are going to be discuss two cases, that E greater than V0 and E less than V0. What do you mean by E? Here E is nothing but the kinetic energy of the particle which is approaches from the minus infinity to the x is equal to 0. So this is the particle, suppose charge particle or any quantum particle which is approaches to this step, and its energy, total energy, the so called the kinetic energy in this region is represented by E. So here E is greater than V0, that is energy of incident beam is greater than the height of the potential. That means here this side, first case we have to discuss that energy of this particle, whatever we are going to be consider, the energy of the particle, the kinetic energy of the particle is greater than that of the potential, whatever the repulsive force this particle is going to be perceive at x is equal to 0 is greater than that of the potential or that repulsive force, and another one is less than that of the V0. That means kinetic energy will be less than that as compared with that potential. Okay, so two cases we are going to be discussed with step by step. So first case, that E greater than V0. Okay, so this is figure 2 is represents that the flux of particles, suppose a uniform beam or flux of particle, uniform beam of particle, or it can be written as flux of particles having each mass m, kinetic energy E, and here we considered E is greater than V0, moving along x axis from x equal to minus infinity. From minus infinity it is moving towards x is equal to 0, that means towards the potential step, and from x equal to 0 this potential steps extends up to plus infinity. This potential step or this value is extended up to plus infinity. Okay, so from minus infinity to x is equal to 0 the kinetic energy is E, and at exactly x is equal to 0 these particles or the flux of particle is going to be interact with a potential which is represented in figure 2, and the beam here same thing it is written, the beam strike the step at x is equal to 0 which is represented in figure 2. Okay, let psi 1x and psi 2x are wave functions for motion of the particle in region 1 and region 2 respectively. So here as we know that the particle can be represented by the wave function in the quantum mechanics, so the flux of particle also can be represented by the wave function. So as here the situation or in this region 1 the situation is different as compared with the region 2, so let the wave function of flux of particle is psi 1 in region 1, it is represented by psi subscript of 1, and psi 2 is represents the wave function of the particle in the region, or the not particle here, flux of particle, motion of the flux of particles, beam of particles in the region 1 and 2 respectively. Okay, now as we know that any wave or wave function or particle in the quantum mechanics can be represented by the Schrodinger equation, or any dynamics can be represented by the Schrodinger equation, or has to be obey the Schrodinger equation. Okay, so in region 1, that means minus infinity to 0, in this region minus infinity, this is minus infinity. Okay, have to just write minus infinity, from minus infinity to 0 in this region we have to set the Schrodinger equation. We know that in general time independent Schrodinger equation is what? D square psi by dx square plus 2m by h cross square e minus vx psi equal to 0. That is the in general time independent Schrodinger equation we know. Here in this region 1 the potential is 0. Here in this region there is no potential, there is no repulsive force, so potential is 0. Hence in region 1 the time independent Schrodinger equation will be what? Will be d square psi 1 by dx square plus 2m by h cross square e minus vx. Instead of vx I have to write 0, psi 1 equal to 0, because vx equal to 0 in this region. Now it can be d square psi 1 by dx square plus 2m e by h cross square, psi 1 equal to 0. Let k square equal to 2m e by h cross square. Let this is equation number 1 and this is equation number 2. Now put this one here. In this equation number 1 we found the equation number 3, that is d square psi 1 by dx square plus k square dy psi 1 equal to 0. This is a second order differential equation. Now we have to set the Schrodinger equation for region 2. The Schrodinger equation region 2, or the time independent Schrodinger equation. Okay, you have to pause the video and you have to write down the note. Okay, I'm going step by step, so you can easily write the note perfectly. So in region 2 the time independent Schrodinger equation, say here time independent Schrodinger equation in short or with abbreviation I have been written TISC. So here for in region 2 the TISC time independent Schrodinger equation will be d square psi 2 by dx square plus 2m by h cross square e minus v0 psi 2 will be equal to 0, because here vx is nothing but v0 is a constant from x is equal to 0 to onwards. So instead of vx I can write v0, and it can be written as d square psi 2 by dx square plus beta square psi 2 equal to 0. Here beta square is considered as 2m by h cross square e minus v0. Okay, we got the two second order differential equations. For the first region or the region 1, this is the dynamics of the particle, the flux of the particle, and this is the equation number 4 is nothing but the dynamics of the particle flux in region 2. Then after solving these two equations we can found the behavior of the flux of the particle in region 1 and region 2. So first we have to consider region 1 and region 2 solutions. Okay, so these two equations are second order differential equation. So the solutions of the equation number 3 and equation number 4, second order differential equations, the solution of 3 and 4 will be in the form of psi 1. For psi 1 will be a e to the power ikx plus b e to the power minus ikx, and psi 2 will be g e to the power I beta x plus h e to the power I minus I beta x. Because this is a second order differential equation, we know before that this two roots of this differential equation will be plus or minus ik. So for this differential equation, y1 equal to a e to the power ikx and y2 equal to b e to the power minus ikx will be two independent solutions. Two independent solutions whose Wronskian is not equal to 0. Whose Wronskian is not equal to 0. So hence the general solution of this differential equation will be the linear combination of these two wave functions, or you can say two solutions. So that psi 1 here, psi, y1 and y2, the two solutions of this differential equation. So in general psi 1 will be the addition or the linear combination of these two solutions. So psi 1, that is solution in region 1 will be a e to the ikx plus b e to the minus ikx, let equation number 5. And similarly for equation number 2, if we are going to consider, the solution of this equation number 4 will be g e to the I beta x plus h e to the I minus I beta x, let it is equation number 6. Okay. So here a e to the ikx is the wave function of, here I put a arrow mark, means this three words should have to be right, then you have to be write continuously this line. So wave function, so a e to the ikx is represents wave function of incident wave of amplitude a traveling along positive x-axis direction. Okay, because this is a waveform. Okay, e to the ikx means it is itself in the form of cos x and cosine and sine function. E to the ikx is nothing but cos kx plus I sine kx. That means it is a oscillatory equation. Means it is represents a wave. So a e to the ikx is nothing but wave function of incident wave. So and which is traveling along positive x-axis direction, because this is plus ikx means it is along positive x-axis direction, and b e to the power minus ikx is nothing but your wave function of reflected wave of amplitude b traveling along negative x-axis direction. Okay, these all four have been represented in this figure. I will be explained. Wait. G e to the power I beta x, wave function of transmitted wave function of transmitted wave of amplitude g. Here there is no comma. Wave function of transmitted, there is no bracket. Okay, wave function of transmitted wave of amplitude g traveling along positive x-axis direction, and h e to the I beta x is the wave function of wave of amplitude h traveling along negative x-axis direction. Because as it is plus, it has to move along positive x-axis direction. As it is minus, it has to be it is representing that it has to move along negative x-axis direction. So here all the wave functions represents a oscillatory behavior, because it is in the form of cosine and sine form. E to the power ikx means cosine and sine form, and as it is complex. So this will be this can be written as in the form of cosine and sine. So hence this four represents the oscillatory behavior. Oscillatory behavior means wave behavior. So this is the incident wave. You can say that this is the incident wave having the amplitude a. This is the amplitude a, and this is the transmitted wave having amplitude g, and this is the reflected wave having the amplitude b in the region 1. So this is the incident wave, and it is interacted with the boundary, means interacted with this potential. See, at x is equal to 0, a potential starts having the potential how much. Here you can draw this one. How much it will be? V0, Vx equal to Vx equal to V0. So when this wave is going to strike a barrier or a potential or a restriction, then some part of wave is transmitted and some part of wave is going to be reflected, because energy of incident wave is higher than that of the potential. Okay, so here kinetic energy, whatever we have been considered for this case, this is E greater than that of the V0. That means whatever the kinetic energy have by this incident wave or incident flux is greater than that of the V0. So part of the flux can be transmitted, part of reflected. So this is belongs to this wave. This wave represents the reflected wave having amplitude B. This is amplitude B, and this is amplitude A of incident wave, and this is transmitted wave having amplitude J. So in this region 2, this is region 2 and this is region 1. Just write these things whatever I am writing. So in region there is no other reflection, there is no other variation of potential. Okay, so this region 2 is fully uniform. That means this transmitted wave is not going to be reflect somewhere, because V0 is constant in this region. So there is no changes. This wave can be found from where it can be reflected. So H or the reflection in this region is not possible. In region 2 there is no reflection can be possible. Okay, so hence H equal to 0. H equal to 0. This is this expression is represented as along wave function of amplitude A H traveling along negative x-axis direction in region 2. Just write in region 2. Okay, in region 2. Here you just write region 2. Here not required, because here we written transmitted means itself it is in region. Only you have to just this addition that in region 2. But in region 2 there is no reflection. If there is no reflection, so there is no amplitude. H will be 0. So if psi 2 in psi 2, if H will be 0, this term is going to be 0. So psi 2 is only will be considered as G to the I beta x. Let this is equation number 7. Now what we have to do? We have to find out these coefficients A, B and G by considering the boundary conditions. So here these things we have been written that now amplitudes means A, B and G. Amplitudes, now amplitudes in bracket you write A, B and G can be evaluated using boundary conditions. The boundary conditions is what? Boundary condition is that psi 1 at x equal to 0 is equal to psi 2 at x is equal to 0. See, here psi 1 is the full incident wave function or the wave function of the particle in the region 1. In region 1, the wave function, the net wave function, incident and reflected wave, if I am going to consider the resultant of this incident and reflected, then that will be nothing but psi 1. You just see here the incident and transmitted, both the wave are continuous at x is equal to 0. So at x is equal to 0 both are same, and at x is equal to 0 also the slope of psi 1x and psi 2x will be also same. That means the first derivative of psi 1x and psi 2x also equal at x is equal to 0. That means the wave function is continuous. The wave functions are continuous across the boundary, that is across the boundary at x is equal to 0, that is psi 1 at x is equal to 0 equal to psi 2 at x is equal to 0. Wherever I am doing corrections, you just do it, okay. And in case of another condition is that slope of the wave function, that means the so called first derivative is also continuous across the boundary at x is equal to 0. That means d psi 1 by dx at x equal to 0 equal to d psi 2 by dx at x equal to 0. That two things we have to consider, and then we can extract or evaluate the amplitudes A, B and G. Okay. So these two boundary conditions has to be applied for this problem, and we have to find out the so called amplitudes. First we have to consider that is psi 1. Here use A and B for equation number 5 and 7 we found. See, A and B, this A and B is going to be used for equation number 5 and 7. 5 is for the incident or in the wave function for the region 1, not incident, region 1, and wave function of the particle flux of the particle in region 2. Okay, so first we have to consider psi 1 at x is equal to 0 equal to psi 2 at x is equal to 0. What we are going to get? See, at x is equal to 0, if we are going to put, then e to the power 0 equal to 1, e to the power 0 equal to 1. So psi 1 x at x is equal to 0 equal to a plus b will be equal to psi 2 at x is equal to 0 means g. Okay, so a plus b equal to g. Let it is equation number 8. Now consider the B, condition B, boundary condition B, that is d psi 1 by dx at x equal to 0 equal to d psi 2 by dx at x equal to 0. First derivative of psi 1. First derivative of psi 1 we have to take, and we have to consider at x is equal to 0. So first derivative will be how much? I k a e to the I k x plus minus I k into b e to the I k x. First derivative of this one, okay, with respect to x is equal to first derivative of this one. First derivative of this one will be I beta into g into e to the I beta x. That will be I beta g into e to the I beta x at x equal to 0. So we have to put, instead of x will be 0, then it will be 1, e to the power 0 1, e to the power 0 1, e to the power 0 will be 1, and we are going to found that a minus b. These two steps are the simple. So we found a minus b equal to beta by k into g. Let it is equation number 9. By adding the two equations, that is equation number 8 and 9. Equation number 8 we found a plus b equal to g. Here we found a minus b equal to beta by k into g, and we are going to be add both the equation, and we are going to found 2a equal to g plus beta by k into g. 2a equal to g can be taken common from these two terms, and it will be 1 plus beta by k into g. It will be k plus beta by k into g, or g we can be written as 2k by k plus beta into a. Let it is equation number 10. Now put equation number 10 in equation number 8. Equation number 8 is a plus b equal to g. Here we found g equal to this much. We have to put this g value in equation number 8. In equation number 8, here what we are going to get? We can get a plus b equal to 2ka by k plus beta. Okay, or b equal to a can be moved to this side as minus a, and it will be k minus beta by k plus beta into a. Let it is equation number 11. Let it is equation number 11. Now psi 1, we know that it is a e to the ikx plus b e to the I minus ikx. Okay, so here a e to the ikx, b value here we found is how much? K minus beta by k plus beta into a. That value we are going to be put. Then we can found that k minus beta by k plus beta into a into e to the power minus ikx. So a can be taken as common. So it will be e to the power ikx plus k minus beta by k plus beta into e to the power minus ikx. Let it is equation number 12. Okay, psi 2 is nothing but how much? Psi 2 is your g into e to the power I beta x. G value we found here 2k by k plus beta into a. that is equation number 10. So hence psi 2 will be 2k by k plus beta into a into e to the power I beta x. Let it is equation number 13. Let it is equation number 13. Now we have to consider here. You can see one thing, if we are going to be calculate the values by putting the values of k, beta, we can found the amplitude of psi 2. The amplitude of psi 2 will be less than that of the amplitude of psi 1. Okay, that means the wave function whatever we can get in region 1 and its amplitude, resultant amplitude will be greater than that of the resultant amplitude in region 2. Okay, this is the amplitude of region 2, and this here is one amplitude, here one amplitude, and here also one amplitude. That means resultant amplitude means we have to consider the both incident and reflection waves and its corresponding amplitude, that can be found as larger than comparatively with transmitted wave function or region 2 wave function. Now we have to consider the probability current density probability current densities. It is not that probability current densities, IES, probability current densities. Incident beam, what is the probability current density? Then reflected beam, what will be the probability current density, and what will be the probability current density in region 1, and what will be the probability current density in region 2, or the transmitted probability current density, that we are going to be calculate now. So we know that the probability current density as in the formula is IH cross by 2m into psi del psi star by del x minus psi star del psi by del x. Okay, this is the general formula for the probability current density. Now we know that now we have to calculate incident wave. For the incident wave, probability current density will be how much? For that we have to consider psi incident means incident wave function of incident wave, wave function of incident wave for calculation of probability current density of incident wave. And we know that the wave function of the incident wave is nothing but how much? A e to the ikx, right? So now we have to going to use this wave function to finding the incident probability current density due to incident wave. So this will be IH cross by 2m psi in is in the subscript. Here J in means incident wave, probability current density of incident wave. So it will be wave function of incident wave del complex conjugate of incident wave by del x minus psi in star del psi in by del x. Okay, we have to put the value of psi in. Here psi in, here I written psi in or incident wave function is nothing but a e to the ikx. You just put nothing else. So IH cross by 2m, here psi in is nothing but a e to the ikx, and derivative of this one, derivative of its complex conjugate. Complex conjugate means a star, and it's here we can write, and psi in star will be a star into e to the minus ikx. You just write this much. Sorry. So derivative of this one will be how much? A star into I minus ik into e to the minus ikx, right? The minus psi in star means a star e to the minus ikx into derivative of psi in, that means ik a e to the ikx, ik a e to the ikx. So here you can see that a star is a mod square, e to the ikx, e to the minus ikx will be e to the 0, e to the 0 will be 1, rest is the minus ik, and here also we can found a star a will be a mod square and ik will be there, e to the ik minus ikx, e to the ikx will be e to the 0 will be 1, and we are going to be found that it will be I h cross by 2m, I h cross by 2m. Here a mod square be taken outside, and it will be ik minus ik, means minus 2ik, I and I will be I square. Here is minus, will be plus, 2 got cancelled, will be h cross k by m a mod square. This is the probability density for incident wave or incident beam or incident flux. Okay, now we have to consider the reflected beam. For reflected beam, the wave function is this one. Just simple, we have to use this one, this wave function. But reflected wave is propagating along the opposite direction of the incident. So hence, due to the direction is opposite, we have to write minus I h cross by 2m psi r into del psi r star by del r del x, this is del x, okay, minus psi r star, r is in subscript representing reflected wave function, into del psi r by del x. So here wave function is psi r is b into e to the minus ikx, so that implies that you have just write psi r star will be how much, will be b star into e to the ikx. You just write this one. Whatever I am writing extra things, you have also write in your note. That implies this one, you have to just write. So you just put these values, means psi r is this much, b e to the I minus ikx, into derivative of this one will be b star plus ik e to the plus ikx minus psi r star is nothing but b star e to the power b star e to the power ikx, b star e to the plus ikx into derivative of psi r. Psi r is nothing but this much, b into e to the b into minus ik into e to the minus ikx. Here it is written as ikx. Okay, so by solving you can get h cross by m into b mod square. Okay, now therefore net probability current density in region 1 will be how much? In region 1, that J1 means net current density in region 1 will be incident current density minus reflected current density. That means h cross k by m a mod square, whatever we found J in, h cross k by m a mod square, and Jr is nothing but h cross k by m into b mod square. So h cross k by m can be taken outside, a mod square minus b mod square. So h cross k by m a mod square into 1 minus k minus beta by k plus beta whole square. Okay, so it can be taken outside. If a mod square will be taken outside, it will be b mod square by a mod square. So it will be 1 minus b mod square by a mod square. So b by a will be how much? Here we written, see, from equation number 11, b by a is nothing but k minus beta by k plus beta. You just I written, not written, no, you just write over here that from equation number 11, we can found that b by a is nothing but k minus beta by k plus beta. Here b by a mod square will be there, so it will be k minus beta by k plus beta whole square. So this will be nothing but 4k beta by k plus beta square, okay, into h cross k by m into a mod square. So total probability current density in region 1 we found this one. Now similarly, probability current density for transmitted beam. For the transmitted beam we have to use transmitted wave function, and transmitted wave function is how much? That will be psi t. Transmitted wave function psi t is nothing but how much? G e to the I beta x. We have to use this one. You just add in this heading that psi t is equal to g into e to the I beta x. Now by considering this psi t, the jt or transmitted probability current density will be I h cross by 2m. This will be psi t into d by dx of if this will be the psi t, then psi star t will be, that implies psi star t will be how much? Psi star t will be how much? It will be g star into e to the minus I beta x. So considering psi t as g e to the I beta x and psi star t equal to g star e to the I beta x, by on this equation, on this general equation, that is what, j is nothing but I h cross by 2m psi del psi star by del x minus psi star del psi by del x. This is the general. Instead of psi, if we are going to write psi t, and instead of psi star, if we are going to consider psi t star, we have to just put only g e to the I beta x d by dx. So g star e to the I minus I beta x, here I written minus g star e to the minus beta x into d by dx of g into e to the I beta x. By solving, we can get jt equal to h cross beta by m into 2 beta by k plus beta whole square into a mod square. So this is nothing but total probability current density for transmitted beam. Sometimes in exam directly they are asking the problems by considering this equation. So it is better that you can remember the last expressions. Okay, now reflectivity or reflectance coefficient of reflection will be, that is R. So reflectivity or reflectance means ratio between reflection or reflected probability current density divided by incident probability current density. So reflectivity is nothing but probability current density of the reflected beam divided by probability current density of incident beam. That is JR, we found this one, h cross m into b mod square, and J in incident wave, we found current density of incident wave is h cross k by m a mod square. So it will be h cross k by m into b mod square divided by h cross k by m into a mod square. It will be k minus beta by k plus beta whole square. Let it is equation number 14. Similarly, transmittivity or transmittance coefficient of transmission T will be equal to Jt by J in. That means probability current density of transmitted by divided by probability current density of incident beam or incident wave. That will be h cross beta. Here we found h cross beta Jt we found. See, this much is nothing but g mod square. This much is nothing but g mod square. Here you can write itself, it will be better. This will be nothing but h cross beta by m g mod square, because g value how much we found, here you can see from equation number 10, 2k by k plus beta into a. Here you found that 2k by k plus beta into a whole square. Okay, so it will be h cross beta by m into g mod square. Here you can write from equation 10, okay. From equation 10. Now in this way, if we are going to put Jt value as h cross beta by m into g mod square by h cross k by m into a mod square, it will be 4k beta by k plus beta square. Okay, let it is equation number 15. Now the total value, the total coefficient. So from equation number 14 and 15, it can be found that R plus T, the reflection coefficient and transmission coefficient, will be equal to 1. That means how much here you can see that suppose this is the figure. There, here it is not there. Suppose whatever the incident wave or incident flux is going to be interact with this barrier, part of has to be transmitted, part has to be reflected. Okay, so incident wave is the sum of reflected plus transmitted. Is it so or not? It has to be proved, otherwise this mathematical calculation could not be acceptable, because this is one type of conservation law. So here from our derivation, at last we found that R plus T, reflection coefficient plus transmission coefficient, is equal to 1. So from equation number 16 it is concluded that the probability conservation is valid. Okay, now result and discussion or conclusion, whatever we have been discussed in the whole video, in summary what we got, that is the points, some points. These points we are going to be discussed in next class or next video. So I suggest to all of you that up to 16, up to this much, you go through this video. Up to 16, whatever the corrections I have been done, you do it, and you go through this video, and whatever the things or the physics I have been explained, you just watch it, and if any doubt you can contact me, we can discuss. Okay, thank you so much for watching this video. Thank you.